I would like to welcome Jinal Parikh. She is a technology analyst at Goldman Sachs, and she loves reading about interesting technologies. She mentors school and college students and inspiring them towards technology. So I'm going to go ahead and stop sharing. Jinal, how are you doing? You ready?
Yeah, thank you. Hi, and welcome everyone. I'm Jinal, and I'm a technology analyst at Goldman Sachs. So today we're going to talk about how to scale databases and what all do we need to keep in mind when we start scaling our database. So why do we need to scale database in the first place? Sorry. So any application or website, when it sees significant growth, it eventually needs to scale in order to accommodate increasing traffic, the amount of data because that will grow, the complexity of data, and the speed at which it is changing. So it might, your data might reduce, it might increase, and so your solution needs to be dynamic and elastic. Let us see an example. So let's say you build an application which is like a smaller version of Goodreads, and it has when you start it, you start small with kind of a few gigabytes of memory and relational database which has following table structure. So you have a book table which has your book ID as the key, and you have a review table where you have a book ID, user, and his reviews and ratings. So basically in this application, you have lots of books and users who give their ratings and reviews to the books. So what happens when your users and reviews increase? So your data volume increases. Also, as more and more people start using your application, your read and write load eventually increases. Next, if your application needs to continue working even if one of your machine goes down, then you can use multiple machines to give you redundancy. And this is basically fault tolerance. If you have users around the world, you might want to have servers at various locations worldwide so that your network latency is reduced. So with all these in mind, let us see two basic scalability architectures. So the first approach is where you keep using a single machine, but you try to make it more powerful each time. And this is known as vertical scaling. So it is also known as shared memory architecture because you have many CPUs, RAM, and disks which are joined together under one OS. The problem with this approach is that the cost increases. The cost increases faster than linearly as compared to the performance. Also, you have limited fault tolerance. Another approach is you can use multiple machines which have a best price performance ratio, and this is known as horizontal scaling. It is also called as shared nothing architecture because you have independent CPUs, RAM, and disk which are connected by a network. So the shared nothing architecture, it requires the most caution from you as a developer because it has several constraints and trade-offs involved which you need to know about. Now let's look at the basics. Some ways you can achieve scalability, and we'll go in detail over a few. So we have replication, sharding, and caching. So replication is nothing but instead of storing all your data on one database, on one machine, you're going to copy it and store it at multiple nodes. And here, when I say machines or nodes or servers, all three refer to the same thing. They can be used interchangeably. So these machines are connected by a network, and you keep their copies on multiple machines. When do we need to replicate data? So as we saw in our application, to keep data geographically close to our users, thus reducing latency. Next, to increase availability. So even if one of your nodes goes down, you still have other copies available that will make your application running. So your application can still run. Also, you increase the number of machines that can serve read queries. So now you can serve more read queries because you have multiple machines. If you only care about increasing read throughput, then replication is enough, and we don't need other mechanisms like sharding. So replication sounds easy, right? You just keep copying, you keep a copy of your data on multiple nodes. But all the difficulty, it lies in handling changes or propagating changes to the copies. There are three popular algorithms for replicating changes to copies. One is single leader replication, and its diagram is shown here. So in single leader replication, what we have is you have one node which is chosen as the leader, and all other replicas, they're called as followers. And all the writes that are made by the application, they are made only on the leader and eventually propagated to its followers. Other mechanisms are multi-leader and leaderless replication, and you can read more about these in detail. Also, you have gossip protocols, which are like pretty interesting and cool, and they were used back in the 80s for replicating changes to the copies. Replication also brings in several problems, one of them being inconsistency in the database. So what it means is that since you have many copies, each of the copy, some of the copies might have different versions of the same data, and which is why we have eventual consistency in certain models. Other problems also exist, like weakening durability, unnecessary failovers, and split brain, where you have two nodes and both of them believe that they are the leader. These are very interesting problems and you can read about them. Next is partitioning or sharding. So as we saw in our application, as our data set becomes large or for very high query throughput, we kind of break the data up into partitions. And what this means is, let's say you have your data in one database, you break it into pieces so that each row or record that you have, it goes to exactly one partition. And partitioning and sharding, they both refer to the same thing and they can be used interchangeably. And I will use these two terms interchangeably in this talk. So as we saw, you break the data up into pieces. This involves rewriting of the application layer. Partitioning is usually combined with replication so that copies of each partition, they are stored on multiple nodes. And this gives us fault tolerance because if your one partition fails, you still have its copies lying on multiple machines. So your data set has not broken down. Okay, so let's see the different approaches of partitioning data sets. So first is by key range. So what we do here is, for our relational data, we choose a key to partition on. And let's say we choose book ID here. So we choose a key, and then what we do is, on the right, what you see is the different shards, or what we call as the different servers that have your data partitions. So you assign continuous ranges of book ID to each of the partitions, and then since you know the boundaries, so here we have chosen a range of 100, and the boundaries are 0 to 99, 100 to 199, and 200, and so on. So depending on your key, you know the boundaries, so you will be able to assign the partition to that particular row. So let's say we choose 34. Since we know it will fall in the book ID, 34 falls in the range of 0 to 99, it will go to the first shard. Similarly, 101 will go to the second shard, and 250 will go to the third one. Okay. Now, the ranges of the keys, like we had 100, they might not be necessarily evenly spaced because your data might not be evenly distributed. So your partition boundaries, they need to adapt to the data that you have. The advantage of this strategy is that your key range scans becomes easy. So let's say if you have your data where your key is timestamps. So you're storing all timestamps and that is what you partition on. And your query looks like, give me all data for today. So if this data is located on the same shard, then your query becomes really easy. So that is what we mean by range scans. Disadvantage is that if your boundaries, they are not corresponding to your uh, data, which means that if you have not uniformly distributed data, then it might lead to skewed partitions. This strategy is used by Apache HBase. Next, we'll see partitioning by hash of key. So here, similarly, we choose a shard key, and we take a hash function, which kind of takes skewed data and it makes it uniformly distributed. Next, what we do is, now instead of the range of keys, what you assign each partition the range of hashes rather than the range of keys. And then you get a key, you calculate its hash, and then depending on that hash, you assign it the partition. So if we take 34 here, we calculate its hash, which is in the range of 7k. And this range falls in the second partition. So your 34 will be stored in the second shard. Similarly, 101 will go to the first shard, and 250 will go to the third shard. So the advantage of this strategy is that it is good at distributing keys fairly among the partitions, since you're using hashing. But now, since you're using the hash of the key and not the key itself, you lose the ability to do efficient range queries. This strategy is used by Cassandra and MongoDB as well. Okay. Now, people often say that sharding is good since your query load gets distributed across many processors. So let's see. So there are two main approaches of executing queries on sharded database. The first approach is for large analytic workloads, or OLAP, where you have huge queries which are complex. In this case, what you do is you maximize parallelism within each query by spreading the query's work across all servers. So you're simply trying to get that complex query, you break it down across multiple servers, and you parallelize it. In contrast, for workloads with many small queries, which are OLTP. So OLTP queries are queries which are basically like insertion, deletion, updating data, but they affect only a small piece of data. So in this case, we choose a partitioning that allows most queries to go only at a single server. So we kind of scaling our queries here. Since the queries are small, we want them to execute at only a single server. So we'll let's see the second type of queries. Okay, for our book review page, let's say we want to query all reviews for a particular book. And this is a very natural scenario. You just might want to see all reviews for a certain book. So your query will look something like this for a relational database. Okay, you want reviews on all book ID equal to 150. Since our data is partitioned on the book ID as the key, it becomes very easy and the query will go to exactly one shard. Since the book ID is 150, our application layer already knows that it has to go to the second shard, and it becomes very fast. And what this results in is that we can have multiple concurrent queries. So here we see 3 queries, but you can have many, and each of them you can determine the shard, and we have a lot of parallelism here. What if you want to query all reviews posted by a particular user? So now instead of the book ID, you want that give me all reviews for user John. Now in this case, since our data is partitioned on book ID and not on user, the query will go to all shards. And how do we solve this problem? So one of the solution can be that we choose another column. Let's say we choose user here, and we partition on this column differently from the primary key index, that is the book ID that we had. So what we're doing here is that we have a review table. We use 2 copies of the review table, which are partitioned on different columns, and this allows more queries to be executed. Both the types of queries that we saw, they get executed at single shards so that they're faster. And the idea of using this multiple table copies is related to the pre-joined projections of tables used in column stores. And this is based on a research, and you can read more about this, how it's related to the column store projection. I have attached the reference of the paper here. By doing this, what we're doing is obviously we're doubling the storage space and cost of the updates. But if you have a workload which is read dominated, then the trade-off may be worthwhile. What we saw here is for a SQL database, because in SQL database you have primary indexes and secondary indexes common. But for NoSQL, where you do not have so, in that case we don't use this partitioning by secondary indexes. Instead, we use term partitioning, which does not use copies of table, but instead it uses references, and which internally gets to the B-tree indexes. So what happens here is that now, since you have partitioned on both user ID, as you can see on the right, user name and the book ID, your read queries, they go to only one shard. So for book ID 50, since you know it will fall in the first shard, it will go there. And for John's review, since the letter is J, you know the partition, and it will go to the second shard. And since we're using partitioning by two columns, the data in a particular shard is the union of these two keys. It's not the intersection. You have copies, basically. But now your write queries, they go to multiple shards and they have become complicated. So in the example here, we see that if you have a write query, which says write a new review by Sarah on book ID 50. So now you have Sarah, so it has to go to the third shard and make a write there. Similarly, it also affects book ID 50. And since you're storing table copies, you have to go to another shard as well. So we conclude that simple queries that go to only one shard, they scale well. Whereas complex queries that go to all shards, they do not scale. Okay, so caching. We all know caching. Caching involves temporarily storing data that has already been requested, and you store it in memory, and it allows faster access later on. The advantage of caching is that it's easy and it gives you fast read performance. But the disadvantage is that you need to know how stale your data is. Also, cache invalidation is an issue. So now we have seen the basics. We have developed an application and it has reached a really good stage. That is the time when we actually think about scaling. And we do not need to think about scaling right from the start. So there are several options available, and with so many options, it becomes really hard on how to choose the best tool or best data store or best scaling architecture. You have NoSQL, you have SQL, you have document-based, graph-based, and a lot more. So here, we'll discuss the questions that you need to ask yourself and your team pertaining to the application in order to determine the best scaling architecture or the best scaling solution. Okay, so let's look at these. So first, what is the mix of your reads and writes? So is your application read heavy or is it going to be write heavy? Depending on that, you'll choose a read optimized versus a write optimized database. Next is, what is the size of your data? If the data is not huge, an in-memory database would be enough. But if not, then you need to store it on a disk. And if a single machine is not enough to store this entire data, then you might need to go for sharding. Next is the structure of your data and application. So depending on how your data looks, you might go for a SQL store or a key value store or a document store. For our application that we saw, a SQL store is fine. People often say that NoSQL scales better than SQL, and that is not completely true. Yes, NoSQL is simple, It is less restrictive and it can handle large data sets because it provides a lot of flexibility. But choosing SQL versus NoSQL, it also depends on what is important to you and your application. So even huge sites like Stack Overflow, Quora, they use SQL stores, whereas LinkedIn, it uses Espresso, which is kind of a document-based distributed data store. Okay, next, what are your access patterns? And what I mean by access patterns is that your application, it will expand and you'll add new features. And as you add new features, so new queries will arise. And depending on these queries, you can structure what is best for your data set. Finally, what do you already know? So the most important question is, every data store has certain nuances that they don't tell out loud. And if as a developer you are very confident about the data store that you use, since you have experience on it, you will know the in and outs of a data store, and that will help you as a developer because you will be sure of what you're doing. Now the most important question is that what can you tolerate? So you cannot have a perfectly fast and performant application which does everything. You will need to know that what are the trade-offs that you're ready to make. So how slow can your application be? How bad it is if you lose your customers' data? Also, what if your users see inconsistent data? Can you take down your application for a while? So you need to answer these questions, and depending on what you are able to trade off, you can choose what is best. Now, regarding choosing the optimal number of partitions, it is advisable to have neither too less partitions nor too many. And it is a good practice to create more partitions than nodes, because if you add a new node to the cluster, then what will happen is that there'll be less data movement because you don't need to partition a data again, and you will just need to move a partition from one node to another. And this practice of over-partitioning is done by LinkedIn's Espresso. So to conclude, deciding the architecture of systems at large scale is usually highly specific to the application. There is no such thing as a generic one-size-fits-all scalable architecture, And you have to determine what is best for your application depending on your application and your requirements. So, for example, a system that is designed to handle 6 million requests per minute, which is each 1 kilobyte in size, it looks very different from a system that is designed for 3 requests per minute, each 2 GB in size. So even though these two systems, they have the same data throughput, the design looks very different because of what they're doing. So finally, remember that every application can scale, not by choosing the right data store, but by building your application the right way. Thank you.
Very good.
Thank you so much, Jinal. Okay, are there any questions for Jinal? I'm looking here. You guys can feel free to unmute yourself and ask the question or send it through the chat.
I've got a question, which I'll post in the chat. Or should I just ask out loud?
You can just ask.
Okay, so since sharding the database looks like a good solution, why can't developers just create a large number of shards?
So you cannot create a large number of shards because when you do sharding, it kind of also has a lot of management overhead, and it puts a lot of load on your nodes. So basically your application layer, since you're sharding and that process of sharding and maintaining the shards, it puts a lot of load on the application layer. So if you're deciding whether to shard or not and how many shards to create, it is always advisable to look at the cost versus the performance that you're getting. And depending on what is optimal, you can choose any of them.
Okay, thank you.
Okay, I have a question here. You can also send it, just to let everybody know, you can send it on the chat. You can send it to everyone if you like. But we have one question. It says, we saw sharding of an SQL database. What about sharding a key value store? Is it different?
So no, it's not. And the approaches of sharding, they kind of remain the same for both SQL and NoSQL. So in NoSQL, your data definitely looks different from how it looks in a SQL. You have key value or maybe a document-based data store. But there also you choose a key to shard on, and then you have hashing and key range. The second one that we saw, it kind of differs there, as I discussed. There you do not have partitioning by secondary indexes, but you have partitioning by term. And yeah, so the concepts remain the same.